Welcome everyone to Bacon and Eggheads. I'm Naeth Shepherd, and I'm your host for today. À noter pour nous suivre en français, veuillez appuyer sur le bouton de traduction simultanée en bas de votre écran. Également, pour poser des questions à notre conférencier, excusez-moi, pour poser des questions en français, à notre conférencier, ouvrez le panneau de Q&A dans Zoom. To submit questions at any time for our guests, please use the Zoom Q&A panel. In a few minutes, we'll take you out to Dr. Naeth in Edmonton. First, let us honor the Indigenous peoples with whom we live on this great land. We thank them for their contributions to the creation of the country we call Canada. We commit to improving relations between their nations and ours, to respecting their rights and cultures, and to equity and fairness in all our dealings. As we face together daunting environmental challenges, we have no better guide than the traditional values that nurtured their peoples for millennia. Treat the land, the plants, and the animals well, and they will look after you. Today's talk is very much about rebuilding respect for the land, and it's emblematic of much of the work of the 50,000 or so members of the Partnership Group's 21 science and engineering societies. Their research seeks to better understand the natural world and the impact of technologies. The ultimate goal is to map a more innovative, more rewarding, and livable future. It's urgent work supported by major new public and private investment. It's research that involves collaboration across disciplines, sectors, and borders, and that increasingly integrates traditional knowledge. Indeed, some of the more innovative research projects are now led by First Nations. The Partnership Group is a nonpartisan registered not-for-profit. Our Bacon and Eggheads could not happen without the support of the many sponsors displayed on our opening panel. We thank them all, along with the speakers of the House and Senate, who for more than 2 decades have encouraged these monthly discussions. To introduce Dr. Naeth, I now call on Mark Wolf, Chief Technology Officer at Canary, one of Bacon and Eggheads' most valued and long-term supporters.
Thank you, Arnett. Good afternoon and good morning, all. I am Mark Wolf, and I have the role of Chief Technology Officer at Canary. For those of you not aware of Canary, we are a not-for-profit funded by the Government of Canada, and we are all about connections. We connect Canadians to technologies that equip our researchers, students, and startups to excel on the world stage. Together with our 13 partners that form the National Research and Education Network, we connect Canadians to each other and to the rest of the world. Our newly launched Cybersecurity Initiatives program connects Canada's universities and colleges to world-class cybersecurity tools and services, and our Dare Cloud program connects Canadian startups to disruptive technologies. This belief in connections is one of the key reasons that Canary is proud to be a longtime sponsor of the Bacon and Eggheads series, because through Bacon and Eggheads, PAGC is able to connect leading Canadian research and innovations to politicians and decision makers. And there are very likely few points in history where the value of science and engineering has been so visible in our day-to-day lives. And while today that focus is obviously on vaccinations, treatments, and the genetics of viruses, we know that science and engineering offer us a path forward in many other areas critical to humanity, be it food security, areas related to climate and environmental changes, or new approaches to energy production and conservation. So it is my pleasure to introduce today Dr. Naeth. Dr. Naeth holds a litany of roles, including Professor of Land Reclamation and Restoration Ecology at the University of Alberta, Associate Dean of Research and Graduate Studies for the Faculty of Agricultural Life and Environmental Sciences, Director, Future Energy Systems, and Director of the Land Reclamation International Graduate School. Like me, Dr. Naeth grew up in Saskatchewan, and I understand that it was here where her fascination with the relationship between the natural environment and energy production began. Dr. Naeth is internationally recognized for her land reclamation research, and her research has led to policy changes benefiting both the environment and industry, leading to numerous awards and acknowledgments. Dr. Naeth established the Land Reclamation International Graduate School at the University of Alberta as the first of its kind in Canada or the world, thanks to an NSERT Create grant. The school provides collaborative and interdisciplinary training and professional development opportunities to support land reclamation professionals, to enable them to take on leadership roles across the wide range of stakeholder groups involved in land management, be it academia, government, or industry, to ensure the best outcomes for our environment. Please join me in welcoming Dr. Naeth.
Thank you, Mark, for that introduction. And greetings, everyone. It's such a pleasure to be here today and to talk with you about one of my favorite subjects. I thank the Partnership Group for Science and Engineering for their invitation and for the great organizational assistance of everybody that's been part of getting this talk together, especially Natalie and Emma. So thank you so much. And I thank you, the audience, for tuning in today and listening. I acknowledge the hundreds of researchers, students, and administrative personnel that I have the privilege of working with and who also contribute to this dynamic area of research. So to get started, let's take a little dip back in time in the story of energy. Imagine yourself back in prehistoric times. By this time of the day, you'd be out of your shelter and probably be foraging for food. And meeting your basic needs would be the focus of each day, your need for food and water and shelter. Our species at that time would have had very little impact on the environment, and we would be in balance with nature. In essence, we were controlled by the environment. Then we discovered fire, and that changed everything. We could keep warm, keep predators away, cook our food. We can increase the amount of light that we were getting in a day so we could increase our work hours. And with fire as that external energy source, we could move around safely. We could dig into agriculture. We could manufacture goods. We could settle and survive in the most challenging climates and landscapes. And for the first time, we could control our natural environment. We could shape the land, make the world that we occupy today. Now, fast forward to the Anthropocene, where we are today, where human activity is significantly impacting Earth's climate and ecosystems. Our energy systems and the dominance that they have in our lives changed everything again. So we're no longer in balance with nature, and you'll see that energy was the tipping point that took us away from that balance. And what we did has left us questioning how sustainable our future really is. Now, the history of energy is very important to that of land reclamation. And I just direct you to the left side of the screen for a moment, and we'll talk about that. So before the Industrial Revolution, we got energy from mussels, from wind, from water. And burning coal to produce steam and turn engines is what really made the Industrial Revolution possible. And think of everything that changed during that period. Energy sources became more concentrated. Energy usage was increasingly centralized in cities and remade maps across the world. Rural communities were shrinking and urban communities were expanding. Production of goods changed, and so did trade. Policies shifted, politics shifted, and we had new economic winners and losers that were emerging. And most importantly, people's lifestyle and their expectations changed. So the environment was impacted as never before with emissions, waste materials, and infrastructure. Now, over the last century, we have relied very much on large-scale hydrocarbon-dominated unidirectional energy flow. And we're now on a journey to a low-carbon economy, which is not going to happen overnight. Fossil fuels will continue to be necessary. We just simply don't have the infrastructure. We don't have the capacity to jump into full renewables. So we must reduce the environmental impacts of these traditional hydrocarbon-based energies. But at the same time, we need to rapidly work towards renewable technologies and their critical storage and grid infrastructures. Now, to help people transition, we also have to think about the social side of this transition and understand the barriers to acceptance and adoption of these new technologies. Now, you all know this part of the story, not a happy one, that our energy systems have led to climate change, to soil loss and degradation, to water scarcity and pollution, and to species diversity losses. And the choices that we made have led to new challenges, obviously, but they've also introduced a lot of trade-offs that we have to deal with. So, for example, we need to produce food for humans and for livestock, but at the same time, we want to grow crops for biomass energy. We have hundreds of thousands of hectares of disturbed sites that are littered around the planet as a result of our energy infrastructure that need to be reclaimed, but there's a major barrier because they cost too much. And if we're putting too much into that, then what are we not putting money into? So lots of challenges, lots of trade-offs. But let's focus just for a moment to get into the thinking about land reclamation and energy and look at the disturbances that were created by our energy systems. So you're all familiar with these sites, I imagine. They're very common disturbances associated with hydrocarbon-based energy, mine sites, pipelines, well sites. And we see the drastic landscape alterations that they cause. Now, many people actually believe that renewable energy has no major impact on the environment, but it does. And whether it's from solar, from wind, from biomass, like these algae ponds you see on the slide. In fact, the size of these disturbances, including their control systems, is a major environmental issue that we need to deal with. And let's not forget those legacy disturbances that I talked about a moment ago. The abandoned mines, all of this other energy infrastructure across the planet, that land is simply too precious to let disturbances sit without reclamation. So when we think about where we are today, as the human population grows, we actually need every bit of land and we need to reduce our environmental impact. Scientific discoveries are improving health, increasing our lifespan almost every day. But this really means nothing if we don't have a sustainable and healthy planet. And it's land reclamation that will help bring us back into balance with the environment and help us gain control again of the impact that we have on the environment. Now, just a few terms to get familiar with. The term energy system is relatively straightforward. It includes all aspects of energy, generation, transportation, to us, use. And regardless of the type, the source, or the transport mode of energy, the environment is going to be affected. Now, it's obvious a coal mine or a pipeline will have a much bigger impact than a geothermal well or a small solar array, for example, but that well and that array will still impact the environment. And any energy system will require reclamation at all stages of its life cycle. And that includes development, during operation, even exploration prior to development, upon decommissioning, and at the end of life, basically, to ensure that the environment is not compromised in meeting the energy needs that we have as a society. So let's talk for a moment then about land reclamation. Land reclamation is essentially what we do to clean up the messes, to make disturbed land usable again, after whatever human land use we have and even some natural impacts. The regulatory term for what we need to achieve is called equivalent capability. And the reclamation that we would do to the original land base would be called restoration or ecological restoration. And land reclamation itself as a discipline, as a practice, includes many different components. It includes remediation, for example, remediating contaminants in the soil and the water, such as metals and hydrocarbons. It involves rebuilding and reshaping the landscape, filling the mine pits, for example, and also blending that reclaimed landscape into the landscape around that's undisturbed. We reclaim soil, replace topsoil, and in some cases, we even build new soils, and we call those anthroposols. And some of the work that we have been doing has led to their upcoming inclusion in the revised Canadian system of soil classification. So we definitely know we're in the Anthropocene. Now, often this soil building and soil reclamation involves the use of waste materials, which I'll discuss with you a little bit later in the presentation. Reclamation includes revegetation, and that's growing the plants that we need for a particular end land use. And all of this just sounds so simple, but of course it's not. The reclaimed land has to function ecologically, and it has to be resilient in response to the use that we're going to have, the weather, and even climate change. So some of the critical decisions that we need to make in land reclamation, you can actually see in this little diagram, and it's associated with the targets that we're working towards. So if you think of the bullseye as the land before it was disturbed, and the solid red dot at the bottom of the diagram as the disturbed land, the axes on either side reflect how the land will function, how the ecosystem will function, and its structure, or essentially what it looks like. Now, the red arrow is for restoration that I mentioned a moment ago, to take us back to what was there prior to the disturbance. And the blue arrows on the right are for similar land uses, maybe with a different species, plant species diversity. And then the left blue arrows are for changed land use, or alternative states as we call them. And that would be something like taking a mine site that was a natural area prior to mining and turning it into agricultural fields. The green arrows represent no reclamation. And as you can see, things can get a whole lot worse, or they can slowly improve with natural processes, natural attenuation. Now, if done well, land reclamation can have some amazing results. And as you see, our smiling graduate student, Heather, she's happy with the trees and the other vegetation on this oil sands reclamation site. But if you look at the bottom of the slide, done poorly, reclamation can be drastically unsatisfactory. And you can see that depicted there. Of course, that wasn't one of our projects. Now, I'm really excited to tell you about the University of Alberta Energy Systems programs that are at the frontier of energy system transition and land reclamation, and ready to address the multiple challenges that we are facing. Future Energy Systems was funded with $75 million from the federal government, the Canada First Research Excellence Fund. It currently supports over 100 projects, and we have 4 areas of research, each with several themes. One area is to increase efficiency and improve environmental impacts of current hydrocarbon-based energy systems. The second is to address and mitigate environmental impacts of all these energy systems, and they include land reclamation and dealing with carbon capture, et cetera. The third area focuses on renewable energy sources. You can see them listed there: soil, water, geothermal, et cetera, as well as their required infrastructure. And that last area is really addressing how we can best traverse the transition, and includes our social science components, legal aspects, economics, et cetera. Now, the energy systems signature area at the University of Alberta, it's for teaching and research, and it really provides an umbrella under which the activities are focused and coordinated, both for growth and for longevity. It embodies technology, the environment, responsible stewardship throughout the full life cycle, from extraction of raw materials to manufacturing, to transportation, to use and recycling, and to final disposal or end of life. One of the great things about this program, these programs, is that they bring together multidisciplinary groups of people. So we have engineers working with anthropologists, environmental scientists working with economists, and business scholars working with sociologists. And of course, our researchers work with Indigenous communities and other communities, the government, industry, as well as not-for-profit groups to essentially tackle some real problems. Now, our research program has 150 researchers and over 600 highly qualified personnel. These would include the graduate students and the postdoctoral fellows. So we're aiming for 1,000 trainees, and we're expecting they'll spend their careers on energy systems, which will yield 40,000 years of work. They tackle topics from petrocultures to fuzzy sets, nanophotonics to flywheels and soil mites, and obviously too many to discuss today. So we're just going to focus on a few projects and examples that are at the nexus of land reclamation and energy systems, and so critical to shaping our environmental future. Now, I mentioned earlier the large footprints that are an environmental concern with renewable energy systems and their necessary grids and storage. Now, one way to control size is basically to reduce the space and weight of the control systems. So when you think about power from solar panels or from wind turbines, it's obviously not consistent because the sun doesn't shine every day, the wind doesn't blow every day. So we need these very good ways to store energy and a grid system to distribute it. Now, the control systems for management can be huge, heavy, and costly. And Ryan and his team are developing new hardware and software control systems, some that instead of being the size of a car, for example, could be the size of a briefcase. One of the students from this team just spun off a startup company with the Alberta government, and with Alberta government support, and they're aiming to take some of this technology to market where it has potential to seriously change the way we install renewable energy. And another one of these systems and some of the work that we're involved in is vanadium redox flow batteries. And these are a great example of using a waste product from an existing energy system to actually support a renewable system. Vanadium is actually a byproduct or one of the byproducts of oil sands development, but it can also be used to make chemical batteries. So if you picture a swimming pool as batteries, when solar or a wind farm is generating electricity, it can be pumped into this pool and stored. And then when you need the power, you tap into the pool. Now, the great advantage of this system is that it's scalable. So if you have a small renewable installation, such as a single turbine, you might have a kid-sized pool. If you have a huge wind farm, you might need a few Olympic-sized pools. So our researcher, Peter, is currently working with partners to test some of these fundamentals. And now bacteria. Catherine, who's pictured on the right side of the slide, did her PhD in microbiology and biomedical engineering on methanotrophs. This was the first joint faculty degree in our program, so it was very exciting. Now, many of the industrial activities and conversions for biomass to biofuels release methane, and this can be converted by methanotrophic bacteria to biofuels, to biofuel precursors such as ethanol, biofuel jet, and isoprene. The industrial implementation of this process requires understanding the physiology and the regulation of these microorganisms. You can see one of the little guys down on the lower right-hand side of the screen. and they need to be modified essentially to improve productivity. And that's the work that Catherine and her team address. Now, on the other side of the slide, we have our postdoc Gloria, and she's also recruiting bacteria. When we use a hydrocarbon solvent to separate sand from bitumen, it produces a solid waste, eliminating the need for large tailings ponds. So this is great news for reclamation because we all know how challenging tailings ponds can be. But some solvent remains in the waste. And so what Gloria is doing is optimizing bacterial communities to degrade those hydrocarbons. And her breakthrough has led to very rapid bioremediation in some cases. Another example, land and water remediation is very expensive, often energy demanding and difficult to scale up. But by modifying surface and other properties of some materials, we can actually remediate them, use them to remediate contaminated soil and water, reduce greenhouse gases, and increase soil carbon sequestration. So we're currently working on another aspect here to actually desorb these materials. So removing the contaminants that we've actually removed so that we can take these materials and use them for soil reclamation instead of carting them off to the landfill. Ever wonder where the 100,000 tons of chicken feathers we collect each year in Canada end up? If you guessed landfills, you'd be correct, but they don't need to go there. Iram and Mohammed are using chicken feathers to remove contaminants such as arsenic from industrial process water. Now, these feathers are strong because the keratin protein that they're made up of is cross-linked. So when you break down those links, you create biopolymers with a high surface area that can adsorb or basically stick to particles such as heavy metals. And then when they remove the dirty biopolymer, it leaves the clean water. So Chris and Scott are also working on these waste materials such as straw, manure, and wood residue to make biochars or hydrochars that are also low-cost adsorbents. And these projects are in the process of being scaled up from bench to mesocosm, and then they will be incorporated into a constructed wetland that we are planning to build at a local mine site. One of the really underused options in land reclamation is waste. Regardless of the source of information, Canada is among the highest producers of waste in the world. And much of this comes from agricultural and industrial sources, as well as from food waste. But what if we could take those materials and use them in land reclamation? Think of all those materials that are heading to the landfills that we could put to much better end uses. And this could be something like tomato residue generated from all the ketchup that we produce, the spent mushroom compost. And these materials can provide organic content to be used in reclamation to fill mine pits, for example. The cost of transportation is actually one of the main reasons that we're not using more waste materials in land reclamation. Now, novel advances in composting, including adding construction materials such as drywall. Again, we all know how much drywall we produce here in Canada. So initial research demonstrates that drywall compost are appropriate to amend soil to establish native and non-native plant species. And you can see Hélène in the greenhouse at the top with some of the compost material that we were working with. Now, let me tell you about one of my favorite research programs. Some land reclamation techniques seem almost too simple, such as using forest floor material, also known as LFH, woody debris waste, and microtopic variability to reduce soil erosion, to add nutrients, to create safe places for seed germination and seedlings. So we know from our research that some seeds must germinate in the dark and some of them need to germinate in the light. And when we use these materials and the little microsites that you see at the top right-hand or left-hand side of the slide, they can provide both of these conditions. So these materials add plant propagules and seeds for native species that are actually unavailable commercially at this time for ecological restoration. Dean spent his MSc and his PhD working on forest floor materials. So we knew that we needed seed from the seed bank. And this slide clearly shows the importance of reclamation outcomes with appropriate salvage depth and placement depth. So if you focus on the upper left rectangle, that's 10 centimeters of salvage and also 10 centimeters of placement. So the shallower the salvage and the thicker the placement, the better outcome we have for providing these plant propagules. Dean's work on stockpiling these materials was also revolutionary in showing how quickly seed viability can be lost, unfortunately, usually within a year. So this work led to recommendations to industry to change practices, and it can be extrapolated to many numerous other disturbances. And now this is my favorite picture from the long-term work, some of which was conducted by Katrina and Robin. The native species diversity from this piling of woody debris is just phenomenal. You can see the grasses, the forbs, and even some of the mosses. So this was on a sloped area of oil sands, of an oil sands mine, on which we use this woody debris and no seeding. Now, when I first started my career in land reclamation as a graduate student, natural recovery was considered a reneging by industry to meet their reclamation responsibilities. But after decades of research, we know there's a role for guided natural recovery or augmented natural recovery, such as what you see here. So interestingly, we are still learning from nature. Now, it takes hundreds of thousands of years for soil to form, and we know about its almost magical properties, just indicated here with all the microorganisms, etc. Thus, allowing this precious material to be hauled to landfills when it's contaminated, usually within our energy systems, is a practice in desperate need of cessation. Work in our program clearly shows we have the technology to deal with this contamination. It may be costly, but it can be done. Now, when 2015 was declared the International Year of Soil, I really had hoped that it might be the year that we actually end digging and dumping, but that didn't happen. So our work continues. Now, there's so much more that we could talk about today. Growing biofuels on marginal lands and what that might look like, progressive reclamation, brownfield reclamation, reducing some of the footprints that we have from our energy systems. And I can't talk about all of them obviously today, but we've talked about a few of them. Now, I have mentioned a few times the importance of helping people to understand the transition in energy systems and to understand the barriers to adoption. So if we can perhaps help people experience and understand the services that nature provides, they may choose a sustainable future, focusing on the environment when they make their energy choices. And we can learn from Indigenous cultures that exemplify sustainability over centuries, living with Earth in relation and responsibility-based ways. So it was very exciting for me as a person working in land reclamation and restoration ecology to see the United Nations declare 2021 to 2030 as they declared it the decade of ecosystem restoration. And as I said earlier, everything we do to improve quality of human life and longevity means nothing if we do not have a planet to live on. So this was, I think, a really good step on behalf of the United Nations. Now, to end my talk, a few take-home messages. And I really tried to narrow it down to the 3 or 4 messages that are recommended, but I just couldn't do it. I needed to have a few more. So here are the take-home messages, things that we can talk about, things that we need to think about in the work that we do and in our everyday lives. All energy systems will impact the environment. As we move to renewables, we are not reducing or we're not zeroing our impact on the environment. And land reclamation, as I've wanted to point out here today, is critical in all of them. We can reduce environmental impacts and increase efficiencies of the hydrocarbon-based energy that we need. We have new technologies for that, and it's an important thing that we need to do in the upcoming decades and now. We have begun implementation of large-scale renewable energy systems with their critical grids and storage. Partnerships, interdisciplinary teams are needed to address the complexity of this energy transition and to build all of these new energy systems. And support is needed in innovation. And if using an example, just like we needed when we decided we needed a COVID vaccine, everybody working together produced great results in a short period of time. So I think we can look towards what we need to do in reclamation and the environment and our energy systems in the same way. Now, these changes will be disruptive and they're going to happen sooner than we think. In fact, many of them are underway, maybe just in a smaller scale than what they will be down the road. And I want to end by just saying how important these opportunities are for Canada. We have such strong energy expertise. We have companies in all types of energy. We rank in the upper 10, number 1, number 3 in the world for many of the scientific aspects of energy. And most importantly, there's a role for all of us on local, regional, national, and international scales. And so if we have scientists and regulators and policymakers working together with societies and individuals, we can make these things happen. So I leave you with my final comment that the time is now for that kind of commitment and that kind of action. Thank you.
Okay, thank you. I think we've about reached the end of the time for our questions. Thank you everyone for your excellent questions. We're running out of time now, and so we'll be posting the recording from today on our website. So please keep an eye out for that. And I would like to pass the floor now to my colleague, Arnett Shepherd, who will close off the presentation. Arnett, you're on mute.
Thank you, David. Sorry about that. I now invite the Honorable Bruce Stanton, Deputy Speaker of the House, Chair of the Committees of the Whole, and the long-standing member for Simcoe North, to offer our thanks to Professor Naeth.
I having a hard time getting my video here. Seem to have audio here, but perhaps if the host could just allow me to activate the video, you'll be able to see me. There we go. Very good. So listen, good afternoon, bonjour, honorable senators, members, and guests. It's a real pleasure to join you here on behalf of the Honorable Anthony Rota, Speaker of the House of Commons, and the Honorable George Fury, Speaker of the Senate, your honorary co-hosts. Premièrement, je souhaite remercier le partenariat en faveur des sciences et de la technologie pour organiser l'événement aujourd'hui. Une des présentations remarquables a été rendue possible par l'appui des parrains et des commanditaires qui étaient affichés sur vos écrans plus tôt. Aussi, je donne mes compliments à vous, l'auditoire, pour votre participation aujourd'hui et vos questions intéressantes. I'm sure you'll agree with me that today's presentation by Dr. Naeth was relevant and informative to the kind of complex decisions that policymakers are facing now and into the years ahead. And this is really where the Bacon and Eggheads program throughout the House of Commons sitting here underline the critical importance of scientific knowledge, discovery, and research in informing good policy. Finally, I'd like to thank Dr. Naeth for her presentation and responses to audience questions today, and for taking the time to prepare for and share her insights into this vital area of energy and the environment. Dr. Naeth, it was great to have you with us here today. C'était notre plaisir que vous avez nous joindre pour notre petit déjeuner avec des têtes à Papineau. Merci beaucoup.
Thank you.
Our next Bacon and Eggheads is on April 22nd. We are very excited to have Professor Alexandre Blais of the University of Sherbrooke, one of the world's leading lights in quantum computing. He'll discuss the latest progress in unlocking the tremendous power and potential of qubits. He's an engaging speaker. If qubits are a mystery to you, they won't be after his talk. The Bacon and Eggheads Selection Committee is chaired by Professor Natalie Goto of the University of Ottawa. As you heard from Dr. Naeth, taking care of logistics and making us all look good is the partnership group's hardworking office manager, Emma Brown. As Zoom closes, please take a moment to fill out the short survey that comes up and do pass on the word about these events. You can keep in touch with us on Twitter, where we are at Ottawa Eggheads, and on LinkedIn as the Partnership Group for Science and Engineering. Thanks again, everyone.